Hi, in this lecture video, I will be discussing limiting and excess reactants. So what are they and why are they important in chemical calculation and stoichiometry? So when we have a chemical reactions and now that we have to perform the reaction, the first thing that we have to do is gather all of our reactants for the experiments. And as we gather our reactants, we will have some amount of one reactant and another amount of different reactant. So based on the amount of each of the reactant that we have, one reactant may then be referred to as a limiting reactant, whereas the other reactant would then be referred to as the excess reactant. So let's first define limiting and excess reactant. The limiting reactant are basically the reactant that are present in the least or the limited amount in a chemical reaction. And because they are present in the limited amount, they will be completely consumed at the end of the chemical reaction. Versus the excess reactant is the reactant that are present in excess or extra. And because they're present in extra, they will not be completely used up by the end of the reaction. And therefore, there will be some amount that is remaining at the end of the reaction. So it's important that we can figure out which one is the limiting reactant and which one is the excess reactant. So here's an example right here. So what are the limiting and the excess reactants and how much product can be made and how much excess reactant would be left over in the following example below. So let's say here we have a pancake experiment, a recipe how to make pancake. And this is the pancake experiment that we have been covering on the previous lecture video. And here is the recipe. And again, this can be thought as a chemical reaction. So let's say here we have 1 cup of flour and we have to use 2 eggs and 1/2 teaspoon of baking powder. And from all of this amount, we'll be able to make 5 pancakes. So this is the recipe right here. And again, a recipe is very much similar to a balanced chemical reaction. And let's say here in the first scenario, let's say as we perform this reaction and we are now gathering all of our reactants. And let's say we have 5 cups of flour and we have 2 eggs and we have 100 teaspoons of baking powder. So those are the amount that we have. So how do we identify which one will be the limiting and the excess reactant? So here in this case right here, we will then see that based on the recipe, 1 cup of flour require 2 eggs and 1/2 teaspoon of baking powder. And right now we have only 2 eggs. So these eggs right here seem to be the ingredient that we have the least of, right? So in this case right here, this will then be called the limiting reactant. Versus the flour would then be referred to as the excess reactant, because we know that if we were to have 2 eggs, we would use only 1 cup of flour, and right now we have 4 cups of flour. So therefore this we have some of the flour left. And here in this case right here, we can see very easily that we will be using only 1 cup of flour, so we have only 2 eggs. And here in this case, the leftover would then be 4 cups of flour. And similarly with the baking powder. So here in this case right here, the recipe called for 1/2 teaspoon of baking powder for every 2 eggs. And now that we have 2 eggs, we'll be able to use only 1/2 teaspoon of it. So there will be 99.5 teaspoon of baking powder that will be remaining. And here in this case, the baking powder would also be referred to as the excess reactant as well. And now, how much product can we make from here then? Then the answer, here in this case right here, we'll be able to make only 5 pancakes. Because we have only 2 eggs. By the time we finish using up our 2 eggs, we can't make any more pancake, and 2 eggs can only produce 5 pancakes. So there it is. That's how we will be able to figure out what is the limitants and what is the excess reactant and how much product can be made in a chemical reaction. And similarly, if we were to have an excess reactant, we know there'll be some of it that will left behind. So therefore, we should be able to figure out how much of the excess reactant they are left behind as well. And as you can see here, in this pancake experiment, it's quite easy for us to see that there'll be 4 cups of flour that is remaining and 99.5 teaspoon of baking powder that it remains. Now, so why don't you work on this scenario 2 right here before we go over the answer together. So here is the scenario 2. Here in this case right here, again, let's say we follow this same recipe to make pancake. And now we have 5 cups of flour. And we now have 20 eggs and 1/2 teaspoon of baking powder. So here in this case right here, we then see that, okay, 5 cups of flour. If I would have 5 cups of flour and every cup of flour would require 2 eggs, then we would be required to use 20 eggs, right? And I'm sorry, in this case, 10 eggs, right? And now we have 20 eggs. So that means that we have a whole lot more eggs than the flour. And in this case right here, we have 5 cups of flour. So therefore, we need about 2.5 teaspoons of baking powder. And if we were to have up to 100 of it, then that means the baking powder is also present in excess as well. So from this scenario right here, we will then see that this is the limiting reactant, and the eggs would then be the excess reactant, and the baking powder would then be the excess reactant as well. And so now let's talk about the amount that is left over. We will not be having any of the baking powder of the flour that is remaining, because all of it will be used up. And here in this case right here, when we have 5 cups of flour, we be needing 10 eggs. And since we start out with 20 eggs, we have 10 eggs remaining. And as for the baking powder, 5 cups of flour will then consume 2.5 teaspoons of baking powder. So we have 97.5 teaspoons of baking powder that remain. And here in this case right here, the maximum amount of pancake that we can make from this experiment will then be 25 pancakes. Because by the time that we use up all of our flour, we can't make any more pancake, although we still have eggs and baking powder that is remaining. Okay, so it's quite easy for us to figure out how much product can be made, which one is the excess reactant, what is the limiting reactant, and how much of the excess reactant that is left behind. And now if we were to now convert this example right here, instead of making pancake, if we were to now convert this into a real chemical reaction, then it still is as easy as this pancake example right here. Okay, so if we can do this pancake, we should be able to tackle and answer any question when we are given a real chemical equation. And now let's take a look at a chemical reaction to see how a chemical reaction may be similar or different compared to our pancake example. So let's say here we have a chemical reaction, and here is the chemical equation. We have 1A combined with 1B to form this AB products. So let's say that's the valid chemical equation right here. In this case, the reactant A and the reactant B are reacting in a 1-to-1 mole ratio to form this AB product. And now, let's say we now gather our material to do this chemical reaction, and we now have 2A and 3B. So how much product can we make then? And from this amount that we gather, what will be the limiting and what will be the excess reactant? So here in this case right here, based on the equation, we see that the first A, 1A, will then combine with 1B. So the first A combined with the first B. And then the second A will then combine with the second B. And now we're running out of A. So therefore, we can see that basically A will then be our limiting reactant. And in this example right here, B will then be our excess reactant. And we will be able to form 2 of this AB product, right? And we have 1 of this B right here that is remaining. So very easy, right? We'll be able to form 2 products and 1 of the B will be remaining. And quite easy for us to identify the limiting and the excess reactant. Let's now try another reaction. So here in this reaction right here, we have 2H combined with 1O. And these are not hydrogen or oxygen. We just call them H and O as an example. 2H combined with 1O to form an HOH product right here. So let's say this is our chemical equation. So based on this chemical equation right here, we see that H and O are reacting in a 2-to-1 ratio. 2H will react with AB1O. So that's what happened right there. And now let's say here is the scenario. We now gather our H and our O to perform the chemical reaction. And here in this case right here, we were able to gather 6H and 4O. Now, initially, upon inspection, it seems that we have less of O than H, right? Because there's only 4O and there are 6H. So that means that we have small amount of O. So we may be very tempted to say that, hey, O would then be my limiting reactant. But the whole point, but then in this case right here, no, it is not. And the reason why as follow, H and O are not reacting in a 1-to-1 mole ratio. So the mole ratio between the reactant plays a huge role in determining what would be the limiting or the excess reactant. For an example, if we were to follow this again, this chemical reaction, 2H would then combine with 1O. So let's say the first set of H combined with O to form the first product. The second set of H then combined with the second O. And now the third set of H combined with the third O. So we can see we have used up all of our H already to form 3 of this product. And we would still have one of the O remaining. So although O is present in smaller amount initially, but in this case right here, it actually is the excess reactant. Why? It is because the reaction is not, the ratio between the two reactants are not in a 1-to-1 ratio, but in a 2-to-1 ratio. So we need twice the amount of H compared to O. And therefore, even though we have less O, but then it still is the excess reactant. And so in summary, it's very important. So the limiting and the excess reactant are influenced by the reaction coefficient. What is the ratio among all of those reactants? That plays a huge role in determining the limiting and the excess reactant. And second, the amount of product that is produced in a reaction is then determined by the amount of the limiting reactant that we have. Okay, so we have to figure out what is the limiting reactant that we have first, and from the amount of the limiting reactant, that is when we can then figure out how much product that can be formed from it. And here are the solution map how to do chemical calculation or stoichiometric calculation. So again, it's not just we don't start out with just any reactant to figure out how much product will be produced, but we have to start out with the amount of the limiting reactant. Very important, because by the time we use up all of our limiting reactant, we don't have any more reactant left, so the reaction would stop. And therefore, we would only be able to produce certain amount of products based on the amount of the limiting reactant. So the solution map is as follows. First, start out with the amount of the limiting reactant. Let's say we start out with gram reactant. Then again, we have to convert the gram of the limiting reactant into mole of the limiting reactant, because all of the reactants and the products are related in mole-to-mole basis. So therefore, we have to convert all of the amount into mole first by using the molar mass of the limiting reactant as the conversion factor. And once we have more of the limiting reactant ready, we can now use the coefficient from the balance equation to figure out how many more of the product would then be produced. And if the problem were to ask us for the product in gram, then now we can now go and convert the next step, use the molar mass of the product to get to the gram of the product. So that's how we will be able to figure out how many gram of product that would be produced from certain amount of a limiting reactant. And now, we should also be able to figure out how much of the excess reactant that will be consumed, right? Because not all of the excess reactant would be consumed, but then only some of it would be consumed. So how much of the excess reactant would be consumed? Then again, we can do the following. Start out with the amount of the limiting reactant, because we know all of this is used up. So if all of this is used up, how much of the excess reactant would then be consumed? Then the solution map is as follows. First, start with gram of the limiting reactant, convert that into mole. And now, after we get more of the limiting reactant ready, we can now convert more of the excess reactant. How many more of the excess reactant would then be required? By again using the stoichiometric coefficient from the balance equation. And once we have more of the excess reactant ready, we can now convert this into gram of the excess reactant. So that way we can now figure out how many gram of the excess reactant would then be consumed in the course of the chemical reaction. Now, so that would be one way to calculate how much of the excess reactant would be consumed. Another way to also do this is, let's say that if we were to know how many grams of the product would be produced already, again, if to be able to produce this certain amount of product, we would be able to require, it will require certain amount of the excess reactant, right? So we can also go from gram of the product into the gram of the excess reactant that will be consumed as well. So basically there are two ways for us to figure out how many grams of the excess reactant that would be required, by starting from the amount of the products that you produce or the amount of the limiting reactant. Now, starting of this two way right here, starting from the amount of the limiting reactant would be much more reliable, because this is something that given to us, how many grams of the limiting reactant that we have, versus the amount of product that being produced is a calculated value. And so if we were to make mistake in this value right here, then that would also throw off our other answer on this part right here. So thus the more reliable way would then be to start from the amount of the limiting reactant. And so here is basically a step-by-step guidelines how to do certain thing. First, how to determine what is the limiting reactant. So here would be the step how to calculate the limiting reactant right here when you are given various amount of the different reactant. First, find the number of mole of all of the reactant based on the amount being used. So if you are given grams of the reactant, then convert them, all of those amount, into mole first by using their molar mass as the conversion factor. And after we have all of the amount of all of the reactants in mole already, we will then divide the number of mole of each reactant by the coefficient in its balance equation. So once we have balanced the equation ready, what will be the coefficient in front of each of this reactant right here? And again, we saw earlier already that the coefficient from the balance equation can dictate and have a huge influence on what is the limiting reactant, right? So this is actually how we would factor that in, by taking the mole of each of the reactant and divide by its coefficient from the balance equation. And after the division already, whichever reactant that now have the smallest amount, that would then be our limited reactant. Okay, so mole of each reactant divided by its coefficient. After the division, we compare the value, whichever value that is smallest, that is our limiting reactant right there. So that would be one way how to determine the limiting reactant. Now, there is another way right here. So it's the second way is as follows. Convert the amount of all of the reactant into the amount of the product of interest. And whichever reactant that produce the least amount of product would then be our limiting reactant. So basically on this second method right here, we are basically assuming if all of this reactant would use up, how much product can be made. So here in this case right here, if we use up something and we can only make a small amount of product, then that tells us that we will be running out of that reactant first, right? So therefore, whichever reactant that produce the least amount of product of our interest, that would then be the limiting reactant right there. So both of this method right here can be used, and which one that you would use is really dependent on what is the question asking and what are the information that already been made available. So that you would decide between this method or this method right here. The second method is actually a very commonly used method, and it's mainly also answer another question that we'll go over in a little bit. And so now the second part, how do we determine how much product that will be produced from a reaction? And this is a very basic types of questions that students will be asked to do in general chemistry classes. How much product can be made? And so these are the steps how to find how much product can be produced from a chemical reaction. So first, we have to find what is the limiting reactant. So again, we have to follow the step above to find what is the limiting reactant first. And we will then convert all of the limiting reactant into the desired product of what we want. So, and that by using the solution map that we have seen above here already. But we have to start the conversion from the amount of the limiting reactant. And now, so earlier I mentioned about this part right here. This method right here is a method of choice. The reason why as follow: as we do all of this work above here, we would be, and then we calculate what is the smallest amount of product that can be produced. Then that smallest amount of that is being produced right there would also be the answer to this question right here as well. So that's why that this method right here, it basically answers two things in one step. Okay, once we obtain the answer already, it also allows us to figure out how much product that would be produced as well. So again, the reactant that produce the smallest amount of product, then that will be how much product that we can expect to make. And the reactant producing the smallest amount of product based on calculation, that would then be our limiting reactant. And third, another types of problem that we would also ask students to do in general chemistry is as follows: determine how much of the excess reactant that is remaining. So we know that at the end of the reaction, we're not going to use up all of the excess reactant. So therefore, there will be some of it that it remain. So how much of it that it remain? And so we can see that it's not that easy, or it's not that difficult to answer this question right here, because we have done this for the pancake example above. If we can do this for the pancake, then we should be able to answer this kind of question as well, if we are now given a real chemical equation. And here is basically the logic to how to solve this kind of problem. And so we can see that first, calculate how much of the excess reactant that it consumes. We are given an amount of this excess reactant right here, and we want to ask ourselves how much of it would then be consumed. How much can be consumed can be calculated from the amount of the limiting reactant that being used, or the product that you form. So that's how we be able to calculate how much of the excess reactant would be consumed. And the amount that will be remaining would then equal to the original amount, which is a given amount, minus the amount that you consume in the chemical reaction, based on the calculation that we did above here. And that way, we'll be able to now figure out how much of the excess reactant that is remaining. And now, let's try some of this example right here. A solution contains 9.5 gram of silver nitrate is added to a second solution containing 3.42 gram of copper 2 chloride in a grayish precipitate form. So what is the limiting reactant? And again, so here in this case right here, whenever it asks us to do any calculation involving a chemical equation or doing some sort of a stoichiometry, then we have to start with a balanced equation first. So here in this case right here, make sure you are able to write the balanced chemical equation for this and be able to predict the product of this reaction. So silver nitrate, AgNO3, and copper 2 chloride is CuCl2. So here in this case right here, this is a double replacement reaction. So the silver would now be forming ionic compound with the chloride, and the copper would now be forming ionic compound with the nitrate. So here in this case right here, we'll be forming AgCl and copper 2 nitrate. Okay, and so copper 2 nitrate is soluble in water, so it is aqueous, versus the silver chloride is a precipitate. So the gray precipitate is basically the silver chloride precipitate. So here in this case right here, the first part of the question asks us, what is the limiting reactant? And if we were to be looking back on the solution map earlier, so what the way how we would answer this question right here would then be to follow this 3 step right here. So again, so we're gonna try this example right here by following this 3 step right here. Okay. So here in this case right here, to find what is the limiting reactant, we want to start from the amount of each of the reactant and convert them into mole and divide by the coefficient. So here in this case right here, we have 5.98 gram of silver nitrate. And now to convert this into mole, we have to use the molar mass of silver nitrate. And the molar mass of silver nitrate is 196.87 gram of silver nitrate, equal to 1 mole of silver nitrate. and that would then equal to 0.0352 mole of silver nitrate. So that would be the amount of silver nitrate in mole. And now we're going to do something similarly with the other reactant. So in this case, the copper 2 chloride. And we have a 3.42 gram of copper 2 chloride. And the molar mass of copper 2 chloride is 134.45 gram of copper 2 chloride equal to 1 mole. And copper 2 chloride. And again, we have to put gram of copper 2 chloride on the denominator, so that way it will get cancelled out. And solving for this will then equal to 0.0254 mole of copper 2 chloride. So that will be the amount of mole of both of this reactant. And now here in this reaction right here, the silver nitrate and the copper 2 chloride are not reacting in a 1-to-1 mole ratio, but in a 2-to-1 mole ratio right here. So therefore that will be the coefficient in the front of the balance equation. So now we have to take the mole of silver nitrate and divide this by 2. And we have to divide the mole of copper 2 chloride by 1. So this would then equal to 0.0176. And this would equal to the same thing, 0.0254. So here in this case right here, we will then see this is the smaller amount. So after the division already, whichever value that is now smaller, that will tell us that that will be the reactant right here. So now because this has a smaller value, we now know that the silver nitrate is our limiting reactant. So this will be our limiting reactant. And that means that the copper 2 chloride would then be the excess reactant. So that's how we'll be able to answer that question right there. And now part B asks, how many grams of the product that would be expected to form? So here in this case right here, we know that the amount of product that being produced is basically comes from calculation based on the amount of the limiting reactant, right? So therefore we know what is our limiting reactant already. So therefore we're gonna go back to the amount of silver nitrate and start from there to calculate how much product that would be made. Now we can either start from this gram right here of the silver nitrate or this mole that we have computed here already. So it does not matter, whichever way would be the same thing. So but we're gonna start from the mole of silver nitrate that we calculated here, since this would help us save us one step. So we know that the silver nitrate is the limiting reactant, and we have 0.0352 mole of silver nitrate. And again, if you were to start from gram of silver nitrate, that is fine too. We have to do the same calculation using the molar mass as well. And now we can see that from the balanced chemical equation. Here in this case right here, we are solving for the gram of silver chloride, right? Because this is the solid product right here. And right now, 2 mole of silver nitrate will be producing 2 mole of this product. So therefore, for every 2 mole of silver nitrate, it will be producing 2 mole of silver chloride. And now for every 1 mole of silver chloride, its molar mass is 143.32 gram of silver chloride. And from there, we'll be able to now calculate, and it equal to 5.05 gram of silver chloride. So that would be how much of the silver chloride that we can expect to produce in this reaction right here. And I'm going to show you guys the other way of what we mentioned earlier already, that we can actually calculate, use this method right here by converting the amount of all of the reactant into the products and see whichever produce the small amount, that would then be the how much product that we can expect to make. And that will also tell us what would be the limiting reactant as well. So let's say here that if we were to choose that method right here, we'll be converting the amount of both of this reactant right here into the product. Now, so we can On the previous work that we did here, we calculate how many mole of copper chloride already. So I can either start from this amount of copper 2 chloride, or I can also start from a mass of copper chloride. Since I done an example where I start from this mole here already, so here in the case for copper chloride, I'm going to start from the gram. So to give you guys how this work out. So again, it's 3.42 gram of copper chloride. And now I have to do the same calculation of what we did above here. 134.45 gram of copper 2 chloride equal to 1 mole of copper 2 chloride. So you can see it get redundant right here. So this is why not necessary. And now going back to the chemical equation, for every 1 mole of copper 2 chloride, it would then produce 2 mole of silver chloride. And now for every 1 mole of silver chloride, its molar mass is 143.32 gram of silver chloride. And from here, we would then see equal to 7.92 gram of silver chloride. So what this calculation right here is telling us is that if we were to use up the entire 3.42 gram of copper 2 chloride, we will be able to produce this much product. Versus if we were to use up 5.98 gram of silver nitrate, we'll be able to produce this much product right here. So therefore, we can see that the silver nitrate produce less product, right? So that so by the time we make this much product right here, 5.05 gram of the product, will be running out of the silver nitrate. So the reaction will be stopped, right? So in the reality, we'll only be able to make this much product right here. But then the excess amount of copper chloride will not be used up. So not the entire 3.42 gram of the copper chloride would be produced, but only certain amount of it. Good. So again, this is why that once we do this calculation right here, we know that this is how much product that we can make right here. And now the reactant that now producing this amount of product right here, which is the silver nitrate, and that become our limiting reactant. Okay. And now part C asks us how much excess reactant it remain. So we know in the previous calculation that the copper chloride is the excess reactant, right? And we started out with 3.42 gram of it. But we know that not the entire 3.42 gram of copper 2 chloride would be consumed, but only some of it. So how much of it would then be remain? So we need to now do that calculation. And again, so to figure out the excess amount, the equation is quite simple. The excess amount equal to the original amount minus the amount that it consumed in the reaction. So here in this case, this is what we are asking for, and we know that we have 3.42 gram of copper chloride. That is the original amount. And now, how much of it would then be consumed? So we have to calculate this value right here. To figure out how much of the copper 2 chloride would be consumed, we can start from the amount of the limiting reactant. And now say that if we use up all of this limiting reactant, how much of the other reactant would then be required? So here in this case, this is one way to solve it. 5.98 gram of silver nitrate. So this is our limiting reactant right here. So starting from this amount right here, we would convert this into mole. So this is 169.87 gram of silver nitrate equal to 1 mole of silver nitrate. And now we can see that for every 2 mole of silver nitrate, it will be requiring 1 mole of copper 2 chloride, because that would be the balance equation right here. 2 mole of this require 1 mole of that. And now for every 1 mole of copper 2 chloride, its molar mass is 134.45 gram of copper 2 chloride. So this would then equal to 2.37 gram of copper 2 chloride. So this is the amount that will be consumed in this reaction. And now to figure out the amount that remaining, the excess amount, it would then equal to the original amount, which is 3.42 gram minus 2.37 gram. That is the amount that we consume. So we have left 1.05 gram of copper 2 chloride remaining. So there it is. That is some of the very basics chemistry question the student will be asked to do in general chemistry. And it's not that difficult. And anytime that you think doing this kind of calculation is difficult, think of this pancake example right here. If we know how to do calculation involving this pancake, then we can use that as a concept to now help us see and picture of it in terms of pancake and apply that to the real chemical equation, and it would simply just as easy as this pancake.